You may have wondered why some of the interference patterns you see are rows of bright and dark patches, whereas others are circular. And it really comes down to the shape of the aperture that the light is diffracting around. So you can see on the left there, we have two closely spaced slits and they are vertical. Now, the light won't be diffracted in the vertical direction because it's not being constricted in that direction, but because the sides of the slit are close together, the light will diffract around the edges and spread out to make that horizontal row of fringes that you see. Whereas on the right you have a circular aperture, and that means light is being equally constricted in all dimensions, and so it spreads out around the edges of the aperture to make the circular pattern. There are other uses of interferometry. One of them is called Fourier transform spectroscopy. Now, spectroscopy means characterizing the spectrum of a light source. In other words, finding out how much light is being emitted at different wavelengths. To do this, there is a set of mirrors acting as an interferometer between the source and the detector. As one of the mirrors is moved, different wavelengths are transmitted as they get constructive interference in the forward direction. The light is measured as one mirror is scanned along, and the resulting information of light intensity for each mirror position has to be processed with a computer to get what they want, which is the light intensity as a function of wavelength. The algorithm to do this is called a Fourier transform. The example you see at the bottom right there is the light emitted from a butane torch. So this shows what a typical setup would look like. A sample can be put directly in front of the source or in front of the detector. It doesn't make any difference. As one mirror moves forward, the wavelength getting constructive interference in the forward direction scans through a range. The result at the detector is what they call the interferogram. And then a computer does a fast Fourier transform to get the actual spectrum. Now, to take a simple example, let's say we have a source that is giving out 3 individual frequencies of light. And you can see that on the left there as sine waves with 3 different frequencies. So the interferogram you get would be the combination of the waves of the 3 different frequencies, and that would show up as a single waveform as you see right in the middle. Then a computer would do a Fourier transform analysis to get from that waveform to the actual frequency spectrum of the source, which is what you see in the graph at the right.